Hello students, we have already studied Kohlrausch's law. Now we are going to study this applications. What are the uses of this Kohlrausch's law? First is calculation of molar conductance at infinite dilution for weak electrolytes. We know that we have a formula to determine the molar conductance of any electrolyte at different concentration. For example, concentration C, it may be anything. uh, at any concentration. For that we need to know हमें ज़रूरत पड़ती है molar conductance at infinite dilution, that is a very low concentration which is near to zero. So we should know this value and we subtract it from A is a constant and under root of concentration. And we have already seen that in case of this strong electrolyte we get a graph like this. When we plot this molar conductance at the different concentrations with under root of C, we get a graph this, and when we extrapolate it, जब हम इसको बढ़ाते हैं यहाँ पर, we get the value at infinite or at zero concentration. This we get the value of this lambda m infinity. Okay. But in case of this, in case of weak electrolytes, we get a graph like this, which runs parallel to this axis. So by extrapolation, we cannot get the value of molar conductance at infinite dilution, which is very vital in order to determine the molar conductance at different concentrations. So here, what Kohlrausch said that these ions in any, whether it is a strong electrolyte or a weak electrolyte, they contribute their conductance of the electrolyte to the full quantity. So what is the crux of this is that this conductance of an electrolyte is basically sum of the conductances, ionic conductance of its ions, cations and anions. So here we calculate, what we do here, we determine this molar conductance of at infinite dilution of the anions and cations of a weak electrolyte in a strong electrolyte. For example, this hydrogen, it is present in lead acetate, it is present in acetic acid, and as well as it is present in HCl. So we calculate its value at infinite dilution in HCl and substitute that value in acetic acid. Similarly, this acetate ion CH3COH, we calculate this is somewhere other. For example, we have potassium acetate, we calculate there its value and add the value we get from sodium acetate and potassium acetate for this acetate ion and H in HCl, and we add these to get the value of molar conductance at infinite dilution for acetic acid. So in this way we get values from different places and substitute here to get the value of a molar conductance of a weak electrolyte at infinite dilution. So this is the case here. We have some in this way we have calculated the values of some the ionic conductance of some ions. Here, for example, we have H positive is 349.6, sodium we have calculated 50.1, potassium ion is 73.1, and calcium cation it is 119, magnesium it is 160. Similarly, we have determined the value of some anions. Hydroxyl we have 199.1, chloride, bromide, acetate and sulfate. Okay. So here, for example, if we have to know that this of sodium sulfate, for example, we have to determine this sodium sulfate. The formula will be sodium twice sulfate is single here. Okay. So here we have 50 and 0.1 into 2, since we have two ions into 2 plus we have sulfate is 160. So this becomes 100.2 plus 160. With this, when we add, we will get the value of sodium acetate. So by determining the molar conductance at infinite dilution of different ions from their conductance with strong electrolytes, we add these to get for any, whether it is strong or a weak electrolyte, we can determine of any this molar conductance at infinite dilution of any electrolyte. Okay. We have another way of doing this. Let us see. For example, we have here we have this molar conductance infinite dilution of acetic acid CH3COH. We know it is a weak electrolyte, we cannot determine it experimentally. So what we do, for example, we take here, this is ionic conductance, molar conductance of acetate ion, plus we will add to it ionic conductance of sodium positive, plus we will add it to acetic this what is more ionic conductance of H positive. Then we will add it to ionic conductance, molar ionic conductance infinite dilution of chloride. Then we will subtract from it ionic conductance of ionic molar conductance of sodium positive, and again subtract this ionic conductance at infinite dilution of chloride. So you see here we have plus sodium, we have minus sodium, these two are cancelled. Here we have plus this chloride, and we have minus chloride, these are cancelled. So what remains there? It remains here acetate ion and H positive ion. Okay, H positive and acetate, this is the acetic acid. So what we do, we take this is sodium acetate, this becomes sodium. We take the molar conductance of sodium acetate, then we add to it here this H positive and Cl, this becomes HCl. We will add to it molar conductance of HCl, and then we will subtract from this sodium chloride. So by adding sodium acetate, molar conductance at infinite dilution of sodium acetate, plus we add it to molar conductance of at infinite dilution of HCl, and this product of this sum of these from these we subtract molar conductance infinite dilution of sodium chloride. So by this we will get the value of molar conductance of acetic acid. This is the part first, then we will go to another these applications.